Okay. So has everyone got the tube, the PDF of the tube? You can drop a message, or else you can unmute yourself, or you can just use the raise hand option that's available. No, wait, I'll resend the PDF to the group. Okay, I have resent the PDF. Yeah. Now we can begin. So the first lesson of your syllabus is real numbers. So all of us have learned a lot about numbers in mathematics. Yeah. So what are real numbers? Like in this lesson, you're going to learn, like we're going to refresh our memory from the early stages of mathematics up to the O-level standard, right? So let's see what are real numbers. Before we begin, real numbers, we need to know few sets of numbers we were knowing basically. So the first set of numbers is natural numbers. The first set of numbers is natural numbers. So can someone, like, you can give it a guess? What are natural numbers? I don't need the definition. I need some examples. Give me some examples for natural numbers. Like whatever you prefer. Yeah. What are examples for natural numbers? We do, like, even if you do not know anything about natural numbers, just give us some examples. Yeah. 0, 1, 2, 3. Uh-huh. Okay. What about the others? If you are not comfortable with typing, you can unmute yourself. If you are not comfortable talking, you can just type. Let's say, give some examples for natural numbers. 100. Okay, 100. Yes, it is a natural number. Okay, good. So, I'll explain you what are natural numbers first. Natural numbers are the numbers which we use for counting, for the purpose of counting. So, before, like, thousands of years ago, right, people didn't use complex mathematics. For example, they didn't use uh, they didn't even use fractions, like thousands, 5,000 years ago. Like they didn't even use fractions, like 2/3 into 1/4. They have no idea about fractions, and they didn't have the need of using fractions. What were they doing? They were like hunting animals, or they were picking fruits. So for those kind of stuff, they only needed few numbers, like 1, 2, 3, 4, or else they might have needed 100. 100 is comparatively a small number. So natural numbers mean the numbers we use to count. So it starts from 1. It starts from 1 and goes up to infinity. Like from 1 to infinity. 1, 2, 3, 4, 5, 6, 7, and so on. So these are called natural numbers. Right? So if you ask, is 0 a natural number? Okay, I'll leave that question up to you. You guys answer. If yes, just say yes or type Y. If no, just type N. Is 0 a natural number according to your conclusion, assumption? Okay, I have one answer. What about the others? Yeah? Yeah, you guys are correct. I have two. Yes. 0 is not a natural number. So basically, what are natural numbers? Natural numbers are the numbers which we use for counting. So they start with 1 and go up to infinity. Infinity is not a number, it is a concept. But you can keep on counting from 1 till the end of time, right? So that's basically what natural numbers. So in the tube, there's the first topic, the set of natural numbers, and within brackets they have like they have given a symbol for it. So this is the set notation of natural number. So hereafter in your O-levels, if you see something like this, you have to remember they are talking about natural numbers, which means only the basic numbers, even without zero. Like zero is not there in natural numbers. Right? I hope we are clear on what natural numbers are. These are very basic stuff. So I'm not going to take more time on this. Natural number. And then the second set of numbers, they haven't given, like in the tube I haven't given you because in your syllabus it's not given, but you know what are the second set is whole numbers. So if I explain you what is the difference between whole numbers and natural numbers, the only difference between a whole number, between the set of whole numbers and between the set of natural numbers is this thing, 0. Natural numbers don't have 0, but whole numbers have 0. So whole numbers are basically natural numbers, but in addition, there's 0. Is that clear? Yeah. We have completed 2 sets of numbers so far. Good. So natural numbers and whole numbers. Good. The next set of numbers, like I'm going to teach you, like I'm going to explain you one by one, and at the end I'll explain you an easy way to demonstrate, like to distinguish between these numbers. It's pretty easy, like it's not a big deal. The next set, we have given the letter Z, right, or the letter Z. It is for the set of integers. You might have heard of this word, but most of them like think whole numbers and integers mean the same, right? That's not true. Part of it is true, right? I'll tell you what's the difference. In integers, we have whole numbers. Can you see the set is developing step by step? In integers, we have whole numbers, but we also have negative whole numbers. The set of whole numbers is completely positive with 0. 0 is not, 0 is neither positive or negative. 0 has no sign, it's neutral. The other numbers are positive, right? The set of integers have positive numbers as well as negative numbers. The set of integers has positive numbers as well as negative numbers. Is that clear? Okay, good. So hereafter, when I'm asking questions, for the ease of your like for the ease of your chat, you can use these letters to demonstrate. Like if I ask you something like, "What kind of a number is this?" You can simply type Z. So I might know it's an integer. Right? Like this. Okay. Let's fill in the blanks in the table. Most of you might have the PDF and some of you might have the printed copy. No problem. I'll just give you the definitions. You can write them down. I'll even type the definition in the keyboard while I'm telling them. Right? So for the set of natural numbers, you can write count numbers used for counting purposes, excluding 0, which means 0 is not there, excluding 0. So that is the definition. I'll send you the definition. Numbers used for counting purposes, excluding 0. That's for the set of natural numbers. And the examples are as shown in the board. You can write from 1 to any number you like. And the next definition is for integers. We don't have a definition for whole numbers. Like we have a definition. I'll give you the definition, but we don't have a space to write it. definition for whole numbers is all natural numbers including 0. All natural numbers including 0. That's the definition for whole numbers. And the definition for integers is easy. Positive and negative whole numbers. Positive and negative whole numbers including 0. So basically 0 is also a whole number. But we stress that 0 should be included. So these are the first 3 sets of numbers. Now let's move on to rational numbers. These, like from this part, you will have to pay attention because these you already know and this doesn't even take a minute to understand. The concept of rational numbers. So, see, we have like, we started from natural numbers from 1 and onwards and we added 0. So we are a bit complete. And we further added some natural numbers. So the set is almost complete. What is missing? What kind of numbers you don't see in these sets? Give me some examples for numbers you do not see here. Like, don't say 77 because 77 is already, like, must be there. What kind of numbers you don't see here? Yeah. Good. Great. I'm getting answers. Yeah. There's an answer as fractions, and there's an answer as two, like square numbers, I hope. And there's an answer as decimals and fractions. Yeah, perfect. So we didn't yet include decimals and fractions. So we didn't include decimals, fractions, and also we didn't include percentages. So basically all these 3 are interconnected because you can convert a decimal into a fraction, you can convert a fraction into a decimal, and you can convert both of these into percentages. So don't confuse these stuff. These are the same. Like, these are not identical, but they are equal. I'll explain you how. For example, this is a fraction, which is half, right? Can someone say me, how would I write this as a decimal? What is the decimal value of half? Yeah, half means 1 divided by 2, which means 0.5. Correct. 0.5. What is the percentage value of half? Can someone say? How do we write half as a percentage? Great. Nice. Good. Yeah. The percentage value is 50%. 50%. So I'll pause the lesson for a while and I'll explain how to do this for those who don't know how to do this, right? But because it might be useful. In grade 10, you already learned this stuff before grade 10. Let's see. Let's do a quick recap. For example, if there's a number as 0.25, this is a decimal. Now I'm going to show you how to convert these into fractions and percentages. Right? You can write 0.225 as a fraction. If you want to do that, you have to take this decimal point 2 steps forward because in fractions, we don't usually write something like, we write this, but in fractions, we don't write 3.2 over 7. This is not how we write a fraction. In fractions, we normally use integers. We use whole numbers for both the numerator and denominator. So I'm going to make this a whole number. So if I make this a whole number, I'll have to move this 25 2 steps forward. So it becomes like this decimal 2 steps forward, it becomes 25. So I move 2 steps. So in the denominator, I'm going to add 2 zeros. So it's 100 basically, 10 to the power of 2, right? I move 2 steps, so I put 2 zeros. So this is the fractional value of 0.25. So can't this be further simplified? Can we further simplify this? Can we convert this fraction into the simplest form? Yes, correct. So, try converting. Good. I have an answer. What about the others? Try converting this into the simplest form. Yes, correct. Correct. So in order to convert any fraction into the simplest form, we have to divide its numerator and the denominator by the same number. So I'm going to divide these by the same number, which is 25. So I divided this by 25. 25 divided by 25 is 1. And 100 divided by 25 is 4. So basically, this number 0.25 can be converted into a fraction as 1 over 4. Or else, no problem if you keep it like this 25 over 100. No problem. Okay. Now I'm going to show you how to convert this decimal number into a percentage. It's easier than converting into a fraction. In order to convert any number, any decimal into a percentage, what do you have to do? I'll ask it from you. What do you have to do? To convert any decimal into a percentage. Exactly. You'll have to multiply it by 100. Right? So 0.25 multiplied by 100 is 25%. I hope that's clear for everyone, because 0.25 multiplied by 100 means we have to move 2 points forward, which makes it 25%. Great, good. 25%. Now, so we were in rational numbers. So I paused the lesson for a while and showed you how to convert fractions, decimals, and percentage. Decimals, fractions, and percentages. So now you might have got an idea of what rational numbers mean. Rational numbers, right? Rational numbers are the numbers including this integers, like all these stuff, plus these three, plus the decimals, the fractions, and the percentage. The collection of all those are rational numbers. But there's a further sophisticated definition for rational numbers. I'll read out the definition for you and I'll explain it. Let me know if you understood. If you didn't understand, please let me know. I'll repeat it and I'll explain it again. So, you consider two numbers A and B. Right? You consider any two numbers A and B. These numbers are integers. So you know what are integers now. Integers are any number in this set. 0, positive and negative whole numbers. Right? So these two are numbers which are integers. Right? Now I'm going to write these two numbers as a fraction. Which means like I'll write 3 and 5 as a fraction. So A is 3, B is 5. Right? Makes sense now. A is an integer, B is an integer. I wrote them as a fraction. So this can also be written as a decimal. 3 over 5 is 0.6. And this can be written as a percentage, which is 60%. So any number which can be written as a fraction, like, do you understand? If we can write any number as a fraction, we can write it as a decimal and we can also write it as a percentage. Is that clear? If we can write any number as a fraction. Yeah, good. So I'll give you a number. I'll try writing this number. Try writing this number as a fraction. Try writing this as a fraction. I taught you first how to convert a decimal into a fraction. So using that logic, you can try this. I'll give you time, give it a try, and try writing this as a fraction. Great. Yeah, I've received an answer from Kavisha. Yeah, that's correct. What about the others? Kavisha or Kavisha? Sorry if I pronounce it wrong. Good. Okay. So, shall we see how to do that? We've got answer. 3.5. 3.5. First, to convert this into a fraction, you have to make this a whole number. So 3.5 is not a whole number. So I'm going to move this decimal 1.4. What happens? It becomes 35. So I have to put a denominator now. I moved it 1 point. So I'm going to put only 1 0 in the denominator. Is this clear? Everyone, is this clear? So these are the basics. So we have to work out the basics in this first lesson. So it will be easier for us. Yeah, good. So we don't have to stop from here because we can further simplify this. We can divide these by 5 now. So how many 5s are 35? 7 5s are 35 and 2 5s are 10. So the answer would be 7 over 2. You can keep it as 7 over 2 or else you can convert this into a, okay, like we don't usually keep a fraction like this. What do we do? Let me know. What do you do for fractions like this? Exactly. So this is an improper fraction. Improper fraction. So I'm gonna convert this into a mixed fraction. So like the easiest way is to check how many twos are there in 3. So this is how I do and how I teach my students in the physical classes. How many twos are there in 7? 3 twos. Okay. 3 twos. And 3 times 2 is 6. No? So 1 remains. The remainder, we'll put it above. The denominator doesn't change. Right? So 3.5. The answer is 3.5. So we converted 3.5 into a fraction. So now I guess it's clear to you that any number which can be written as a fraction can be written as a decimal and also as a percentage. So rational numbers mean all the sets of numbers mixed together. Fractions, percentages, decimals, whole numbers, and everything. Positive, negative, everything. Everything we learned up to this point. Is that clear? Okay. And the notation, like we were writing some notations, some letters for the sets. For the set of rational numbers, we use the notation Q, right? Q is used for the set of rational numbers. So for the set of rational numbers, we can like I'll write it here. Examples for the set of rational numbers. I can write minus 77, minus 32 over 7, minus 0.35, 0, positive, like I'll just write 11. I can write 11.5. I can write 3 over 2. Anything, any number you wish. Any number you have learned up to now is the rational number. This is the rational number. This is the rational number. This is the everything is a rational number because this is the largest set, right? This includes everything. Okay. Now, before moving on to the next topic, let's write down the definition for rational numbers. I'll type it out. You can write it down. The definition for rational numbers. if A and B are two integers, if A and B are two integers, the number A over B, which can be represented as a ratio, is a rational number. So I typed out the definition, and in the definition you can see I have used the word ratio because ratios are also fractions. Basically, something you write 7:4, you can write it as 7/4. You'll see in the coming lessons. There's a lesson called equiangular triangles. It's in the second term. So in that lesson, you can see how to you can use ratios as fractions. You can see that. So the name rational comes from the word ratio. Right? So if we write A over B, this is a ratio. That's why they are called rational numbers. Now, I told you in the beginning, I'll teach you an easy method to find out which number is which, like to memorize, don't memorize, to keep in mind how the number set evolve. Okay, this is how. The easiest way is you take a number line, right? And the basic numbers we study from the number line are 1, 2, 3, 4, and so on. So these are called natural numbers, the set of natural numbers. 1, 2, 3, 4, and so on. If you add a zero to it, now what does this set become? Let me know. What is this set? Exactly, W. It's the set of whole numbers. So now it is the set of whole numbers. And now I'm going to add negatives. Negative 1, negative 2, negative 3, and so on. Now what is this set? Yeah, good. Now this is integers. And the numbers in the middle of these, like 1 and 2, in the middle of 1 and 2, there's 1.5. In the middle of 2 and 3, somewhere we can write 2.9. We can write in the middle of 1, 0 and 1, I can write minus half. Okay? This is a fraction, this is a decimal. So all these together form the set of what? Great. Form the set of rational numbers. So this is how to keep it in mind. Just draw a number line. 1, 2, 3, 4 is natural. If you add a 0, it becomes whole. And if you add negative numbers, it becomes integers. And if you add decimals and fractions, they are rational numbers. So everything you can see here is a rational number. Everything. Even 0 is rational, 1 is rational, everything is rational. Right? Okay. We are almost over with the theory. There's a last set of numbers, and then we are done with the first part of the lesson. Right? Good. So the next part is irrational numbers. So there's something as rational. The complement of it, which means the opposite of rational, is irrational. Okay, so when I teach to keep irrational numbers in mind, I tell the students that those are ugly numbers. What are ugly numbers? For example, okay, I'll start with a rather beautiful number. What is this number? Yeah, good. So 22 awesome. Yeah. What is it called? What's its name? Yeah, that's pi. Okay. So this is pi. In your syllabus, we give it the value 22/7, or else we give it the value 3.1, right? But actually, like, I don't know how many of you knew this before. This doesn't end here. Like, it's not 3.14 and it doesn't end. Like, it's 3.14159, and likewise it continues. It continues up to infinity. Like, it has no end. Pi has no end. For the sake of easiness, for the ease of calculations, they have represented pi as 22/7 or as 3.14. But in real world, actually, we cannot represent this as 22/7. You understand? For example, let's leave pi alone for a while. And if I ask you, what is the value of this? Yeah, pretty easy, right? 2. What is the value of this? 3. Yeah, simple. Okay, now let me know what, if you know, what is the value of this? You can even use the calculator. That's not a problem. The square root of 6. Yeah. The calculator will give you an answer somewhere around 2 point something. 2 point, like, I'll just give you an answer 2.345, something like this. Because we know the square root of 4 is 2 and the square root of 9 is 3. And the square root of 6 must lie between, somewhere between 2 and 3, right? We agree with that. The square root of 4 is 2 and the square root of 9 is 3. But the root of 6, we do not know for exactly, to be exact, but we know it's somewhere between 2 and 3. Yeah. The square root of 6 does not have an exact value. If you check the calc, it will give you tens of 12s of digits, like 2.4719 or something, some sort of numbers. But in reality, this doesn't end. Same like pi. 3.1459 doesn't end. The square root of 6 doesn't end. Because this is not a perfect square. You get it? Like, for example, if I ask you what is the square root of 16, what would you answer? 4. Yeah, that's 4. Because we know if we multiply 4 times 4, we'll definitely end up with 16. We'll end up with 16. But if I ask you what is the square root of 15, make a guess. You just make a guess and tell me, like, 4 point what? Sorry, 3 point what? Square root of 15. Yeah, the square root of 15 can be 3.9, right? Let's check the square of 3.9. Grade 10, unit number 2, square root. You do this first approximation, right? Let's check. 9 times 9 is 81. 9 times 3 is 27 and 8, 35. 3 times 9 is 27. 3 times 3 is 9, plus 2 is 7. 1, 12, 5. See, 15.21. So, someone has sent an answer from the cal. The cal says 3.872 and it continues. Let's check 3.8 now. Let's check 3.8. 3.8 into 3.8. 8 times 8 is 64. 24 plus 6 is 30. 3 times 8 is 24. 9 and 11. 14.4. See, this is less than 15 and this is greater than 15. So the answer must be somewhere between 3.8 and 3.9. Right? So when you check the cal, it says, the cal says 3.872. Even if you multiply 3.872 by 3.872, you won't get 15 to be exact. Like even if you take 100 digits from here and multiply it by the same number, you won't get exactly 15. Right? Not 100. Even if you try a million digits, you won't get 50. You'll get something like 14.999. Yeah, that's possible. But you can't get to 50. That's why I say they are ugly numbers. But because they don't have an exact value. Like they keep on going, and that makes no sense. Now do you get an idea about irrational numbers? They keep on going and there's no pattern even. Right? Do you get an idea? Yes. Okay. Once more, coming to this number, pi. Started from here. So pi is an irrational number. Pi doesn't have the exact value of 3.14. Now, in the exams, you must use this 22/7. We are using this for the sake of easiness of calculation. But to be exact, this is not the value of pi. So pi is something 3.14159. In YouTube and all, if you like search for the first 100 digits of pi, they'll show you the first 100 digits. It goes on, like it doesn't stop at 100, it doesn't stop at even a million. They're still finding the remaining digits of pi. Right? That's why this is irrational. And I'll ask you a simple question. Now you know what are rational numbers and what are irrational numbers. Now tell me, out of root 7 and root 25, what is rational and what is irrational? Exactly. Root 7 is q dash, which means root 7 is irrational. Because this is 7 is not a perfect square, right? 25 on the other hand, it is a rational number, right? What is the square root of 25? Exactly. The square root of 25 is 5. So this is rational and this is irrational. If you have any doubt regarding these two numbers, just let me know. I'll re-explain the concept of rationality and irrationality. Yeah, are we clear now? Okay, everything is clear. Good. Before we move on to real numbers, the topic of the lesson, I'm gonna tell you again. You learned that pi is 22/7. So I told you this is a lie. Like this is lie means this is not true, to be exact. So we can't write pi like this. So can you understand why is it irrational? This is not the exact value of pi. If we can write pi like this, that is a rational number. Right? If we can write pi as 22/7, it can be written as a fraction, so it is rational. But pi is not rational. It cannot be written like this. But for the sake of your exams, we have to write as 22. I hope that is clear. Now, the final question I was about to ask. This number, is it rational or irrational? Yeah. Yeah. you guys try this. There's a question. The question is, so if they ask you the square root of a perfect square, is it rational? Yes, the answer is yes. If they ask you the square root of perfect square, the square root of 36 is 6. So that is rational. Because we can represent 6 as 6 over 1. This is a fraction. Or else we can represent 6 as 12 over 2. 12 divided by 2 is 6. So 6 can be represented as a ratio, as a fraction. Therefore, it makes it an rational number. Because this is already an integer, so that's definitely rational. Yeah. So for this, I have got an answer. Someone says this is irrational. What about the others? Irrational. There are two answers as irrationals. Yeah, three. Good. So now, if I say that this is like you guys say this is irrational, right? Okay, let's for the sake of argument, let's agree this to be irrational. Now, I need you guys to find me the value of this. You won't need the calculator for this. If you need the calculator, you can use it. Try to find the value for this. But the calculator, but you are accurate than the calculator. So it's better if you can do long division or something to find the value of 1 or 2. So these are integers, right? So this is a rational number. I need you to find the decimal value of this number. Good. So now I'll repeat the same question. Is this a rational number or an irrational number? Yeah. Look how the tables have turned, right? Yeah. So now all of a sudden becomes rational. So you might be confused because I told you that pi is not rational because it has unending digits. Yeah. Yeah. I didn't tell you something. Pi has unending digits. Like I'll write some digits of pi for like this is not true. Like I'm just improvising. Okay. And I'll write this 0.33333. Right? Both of these are continuing till infinity. But which is nicer? Like I'm not talking maths here. Just look at them, 1 and 2, which is easy to see or easy to remember. Which is nice, 1 or 2? 2 is nice. Yeah, because they have a pattern. There's a pattern, right? There's a pattern. So the numbers which repeat, the decimals which repeat but have a pattern are also rational. For example, if there's a decimal like this is repeating, this is recurring, this is occurring again and again, this is repeating, but they have a pattern. 1, 2 is repeat. But if you take something like this 7.134512107910, there's no pattern, right? So 1, 2, 3, 4. Out of these 4, what are the irrational numbers? One and 4 are irrational, right? This is irrational and this is irrational. These two are rational. These two can be represented as fractions. We saw that 0.33 can be represented as a fraction. So no doubt, the numbers which repeat but have a pattern, somewhat of a pattern, is a repeating decimal, so it is rational. Now, this is the full concept. Now, do you understand the difference between a rational decimal and an irrational decimal? So the way of finding them in decimals, that's not in your syllabus, right? Like they never say you ask you to convert this into 0.3333. They won't ask you to convert this into a decimal because it takes a bit of algebra. Like this, you already know 0.33 is 103. Or else, if they give you something like this 4 over 3, like 1.33, that must be 4 over 3. But you don't have to remember these because they won't ask in the exam, because that requires, like, we have to consider 0.1212 to be x, and we have to find 100x, and it is a tedious job, right? So they won't ask you this. So you won't have to practice this. If you need them, I'll make a separate session for that because that is out of syllabus. And let's convert recurring numbers into fractions. Okay, that's a good question, by the way. Okay, now we are almost done. Back to our number line. In our number line, we first started to write 1, 2, 3, and 4. So these are natural numbers. And then we added 0, which made it whole numbers. We added 0 to make it whole numbers. And we included negative numbers too. So which altogether made this the set of integers. And finally, we did 1.5, 2.5, or as negative 2.5, 1 over 2, minus 1 over 2. So these kind of numbers, they are rational. And we took pi, root 2, root 3, the square root of 2 and 3, the square root of 7, the square root of 11. All these non-perfect squares are irrational numbers. Right? So these numbers, you might have a doubt. I'm gonna go the extra mile. I'm gonna like go somewhat out of syllabus and teach you, because I represented every number in the number line, but I didn't represent these stuff in the number line. So I'm gonna teach you how to represent these in the number line. But they won't ask you in the exam. Right? For the sake of my satisfaction, I'm gonna teach you how to represent a number like root 2 in a number line. It is done like this. I'll take a plane. So what is this plane called? Grade 10, grade 9 to do graphs on this. Yeah. It is a Cartesian plane, right? So in the Cartesian plane, I'll construct a triangle, right? A triangle using 1 unit as the length and 1 unit as the height. So this is the triangle. This is my triangle. Length is 1 meter, height is 1 meter. So what would be the angle here? What would be the angle? Exactly. The angle would be 90 degrees. So which makes it a right angle triangle, right? It's a right angle triangle. So if I draw this right angle triangle, what is this side called? See, you are revising every chapter in your grade 10 journey. What is this side called? It is called the hypotenuse. Exactly. It's called the hypotenuse or the hypotenuse. Right? So to find the value of the hypotenuse, which theorem should I use? Exactly, the Pythagorean theorem, or else the Pythagoras theorem, right? So using the Pythagoras theorem, I'm going to find the hypotenuse. So we know Pythagoras theorem, a square plus b square is equal to c square, which means the square of 1 plus the square of 1 is equal to c square. The square of 1 we know, the square of 1 is 1. Again, the square of 1 is 1, which is c square. Now, what is 1 plus 1? That is 2. The square of c is 2. Now, if I want to find c, I have to take the square root of this side. No? So, c is the square root of 2. Do you see where I am getting to? C is the square root of 2, which means this length is square root of 2. Right? So, if I took this length and if I lined it up on the number line, I can't do that on the whiteboard. If I had a smart board, I would have done that. I take this line and keep it on the number line. It must be somewhere here. No? So that is the value. That is the value of the square root of 2. That is the value of the square root of 2. Now is it clear? Like it was not necessary, but for the completion of the lesson, I needed that. You don't have to remember that, but did you get an idea of how to represent? Okay. Others? Okay, I'll repeat it for you. See? Again, you know how to represent any rational number on a number line. But if they ask you to represent an irrational number, you draw a Pythagoras theorem, like you draw a right angle triangle which has 1 meter in length and 1 meter in breadth. So to find the hypotenuse, you will have to use the Pythagoras theorem, like I did here. The video is being recorded, so you can rewatch how the steps are done. So the length of the hypotenuse is the square root of 2. So now this length is root 2, right? This length is the square root of 2. So consider this to be a stick or something. If I take this stick and if I keep this on the number line horizontally, the stick will align somewhere like this, no? Roughly somewhere like this. So this would be the value of root 2. It is greater than 1. It is somewhere around 1.414. Right? That is the square root of 2. So that is how you represent irrational numbers. But again and again I'm repeating, this is not in the syllabus. All we have to understand is up to the number set from natural numbers to irrational numbers. Now is everyone clear from natural numbers up to irrational numbers? Okay, great. Good. Now we'll write the definition for irrational numbers. We'll write the definition. I'll type out the definition. Any square root of a non-perfect square, any square root of a non-perfect square, and the value of pi are examples for irrational numbers. This is one definition, and there's another definition. You have to write both of them. And now the definition I'm giving you now is the exact definition. Any number which doesn't belong to the set of rational numbers. So any number which doesn't belong to the set of rational numbers is an irrational number. Okay, so I hope we can move forward. Now is when we get to your topic, unit number 1, real numbers. So basically, what are real numbers? Any number you learn in the syllabus is a real number, which means any number which is rational or irrational, any number which can be represented on a number line is a real number. So this is no big deal. The lesson is about the numbers you are going to use in your O-level syllabus. Right? So any number which can be represented on a number line is a real number. I hope we are clear, and I hope first part of the lesson is clear. Yeah, good. So this is the theory. Now we will have to do some questions, right? Before moving into questions, yeah, we can. You guys can try the question number 11 on page number 6. That's just true or false. True or false, right? So let's try that. There are 15 true or false questions. I'll give you around 10 minutes. 10 minutes is too much for this, I guess. It's okay. If the answer is true, just put true. Like in the chat, you can write number 1, P, number 2, F. Likewise. Take your time. Your time starts now. In 10 minutes, I'll be checking your answers and let's discuss the answers. For those who do not have the tute, I'll display the questions in the screen. Give me a minute. Oh, guys, wait a minute. I didn't teach you what are terminating decimals yet, right? So, the fifth question and the ninth question cannot be done yet, right? It has skipped the fifth question and the ninth question. I'll teach you what are terminating and recurring decimals. They are in the table. I skipped them. The fifth question and the ninth question. For now, leave them. Don't do. Others, you can try and give me the answers. Yes, guys. Question number 7 and question number 11 are the same question. It has been repeated. It's a mistake. Good. I'm receiving answers. There's another minute left. In 1 minute, let's start discussing. Good. Let's see. Okay. Let's discuss. So the first question. Now, I saw answers from 2, 3 of you. The others also. Just give an answer for the first one. There's an integer between two consecutive integers. Okay, let's see what are integers we know. The notation is Z. Integers means positive and negative whole numbers, right? Including zero. Positive and negative whole numbers, including zeros. So they are saying that between two consecutive integers. I hope you guys know the meaning for the word consecutive. The letter consecutive to A is B, right? The letter next to it. So if I take two consecutive integers, is there an integer in between these two integers? True or false? Yes or no? Is there an integer in between these two? No, right? There can be numbers, there can be rational numbers, there can be irrational numbers. But integers, that word is important, right? Integers are not there. Give me a minute. I'll be back in a minute. Okay, I'm sorry for the delay. So in between two integers, there cannot be an integer, right? In between two consecutive integers, there cannot be integer. I hope that is clear, right? Okay. Roman number two. Roman number two. All negative numbers are integers. Is it true? All negative numbers are integers, or is it the other way around? So none of them are true, because if they say all negative numbers are integers, so okay, is this an integer? Is this an integer? -7. Yes, -7 is of course an integer, right? But they say all negative numbers. So if I ask you, is this an integer? No, no. So we can't say that every negative number is an integer. Some negative numbers are integers, like -7, -100, -75. Those are integers, but not all, right? I'll be back. Okay, I'm sorry again. So the answer for the first one is false, and the answer for the second one is also false. Fine. I hope you're clear. Yeah. Okay, the third one. Between any two rational numbers, the answer for the first one is false. Yeah. Between any two rational numbers, there's always a third rational number. Is that true? Between any two rational numbers, we can take any two rational numbers, 7 and 10. Between any two rational numbers, there's always a rational number. Is that true? See, 7 is a rational number, 10 is a rational number. So between 7 and 10, there's 8, there's 9, there's 8.5, there's 9.5. Yeah. So between any two rational numbers, there's definitely rational numbers. Even if I take this, right, you might not notice this. Even if I take these two numbers, there's a number between them because I can write 1.55. 1.55 is somewhere between 1.5 and 1.6. Do you get it? Is that clear? Yes. See, even if I take this 0.99, and if I take I'll take 0.98 and 0.99, even in between these two, right, I can write 0.981, 0.982, 0.983, 0.984. I can continue. That these numbers are in between these two numbers. So rational numbers, no problem. In between every two rational numbers, there's definitely rational numbers. Okay, I'll ask you a simple question. It won't seem that much hard, right? But you'll have to think before you answer. How many numbers are in between these two numbers? How many numbers? Not integers. We know there's no integer in between these two. How many numbers are in between these two? Okay, there's an answer. Around 10. Okay, there's another answer. Yeah, it's worth trying. Like you're giving it a try. So that's the best thing. You don't have to get the answer correct, but at least you tried it. Yeah, there's another answer. Good. That's it. In between these two, I can say in between 0 and 1, I can say 0.1, 0.2, 0.3, 0.4, 0.5. Up to 0.9, I can keep on going. So there's 9 numbers, 0.1 to 0.9. Then it's 1. And if you can see, in between these two, I can write 0.11, 0.11, 0.12, 0.13. And also, in between these two numbers, I can write 0.01, 0.001, 0.0001. Can you see? How many numbers can I write? How many numbers can I write? Exactly. I can write an infinite amount of numbers. I can keep on writing because I can add infinite number of zeros, right? I can write infinite number of zeros. I hope it's clear. So in between two simple numbers, see, in between 2 and 3, there's infinite numbers. We might have not think like we might have not thought about this in such a perspective. We just consider 2 and 3, those are two numbers. There's no number between them. Might be 2.5, 2.3, that's all. But in between these two, there's infinite number of numbers. All those numbers can be represented on the number line. So they are rational and they can be irrational. So altogether they are real numbers. That's what this lesson is about. Not just theory. You'll have to apply this and you'll have to see the beauty of maths. Right? Okay. And the fourth one, it's an interesting question. Fourth one. All integers are rational numbers. Is that true? All integers are rational numbers. All integers are rational numbers. Yes, that's true. Because if we draw a Venn diagram, in the beginning there's natural numbers, which means 1, 2, 3, 77, like. And then we add 0 in natural numbers. We added 0 to make it a set of whole numbers. And then we add negative numbers. We add negative numbers to make these integers. Right? And then we add decimals and fractions and whatnot. We add decimals, we add fractions, everything. We add percentages, everything to make this rational. Now see, the set of integers is inside the set of rational. The set of integers is inside the set of rational numbers. So every integer is a rational number. But if I ask you, every rational number is an integer, is that true? Every rational number is an integer. No, that's not true because rational numbers are outside the set of integers. So there can be numbers which are not integers, but they are rational. Right? And then if you want to complete the Venn diagram, you can draw a universal set. The universal set is real numbers R. The universal set is real numbers. So I'll ask you a simple question. What is in this area? What is in the shaded region? What numbers? What is the answer for this? Exactly. If this set is rational, very good. If this set is rational, so outside that, that is Q dash, right? Q dash. This is irrational. This is irrational. And altogether, every number in this inside this, we call them real numbers. Good. Good that you understood. Okay. The answer for the second one is false. And the answer for the third one is true. The answer for the fourth one is also true. Okay. The answer for the sixth one. They have asked the question I asked you before. The answer for the sixth one is then false. Right? How about the seventh question? What about the seventh one? Root 3, the square root of 3, can be expressed as a rational number. The square root of 3 can be expressed as a rational number. Is that true or false? The square root of 3. No. Okay, the square root of 4, this is definitely rational because the square root of 4 has an ending value, right? But the square root of 3, is this rational or irrational? Does this have a perfect answer or not? That is irrational. That is irrational. Right? Square root of 3 is an irrational number. Right? All this time we were talking, if it is a perfect square, it is rational. If it is not perfect, it is irrational. So the answer for the seventh question is wrong, false. Right? Root 3 is not a rational number. Root 3 cannot be expressed as a rational number. So the easiest of questions from this set is the eighth one. The answer to which is, what is the answer for the eighth one? Correct. 0 is a whole number because we had the set of natural numbers and we added 0 to it to make it a whole number. So that's true. Good. Yeah, ninth one I told you to skip. Okay, X, the 10th question. Is that true or false? The 10th question, is it true or false? True. Okay, I have an answer as true. 3 answers as true. That means you guys have understood the assignment. What do they say? No. They say sum of two rational numbers can never be an integer. Let's see if that is true. Okay, you guys give me an example for rational numbers. Give me two rational numbers to add. Give me two rational numbers. I'll add them up and see if they can be integers. So these are irrational. Square root of 3 and square root of 8 are irrational. They are talking about rational numbers. Rational numbers means integers, whole numbers, decimals, and whatnot. So rational numbers you can take 7.3 and 2.1. These are rational, right? They are rational. So if I add them, I'll get 9.4. So this is not an integer. Yeah, that's true. This is not an integer. So if I add these two rational numbers, I didn't get an integer. But using this, can I say that if you add any rational numbers, if you add any two rational numbers, you can never make an integer. Can I make that claim? If I say to you, whatever rational number you take and add, you can never make an integer. Is that true? That's not true because give me the answer for this. Give me the answer for this. What is 0.2 plus 0.8? 1. So is 1 an integer? Yeah, 1 an integer. 1 is an integer. So see, I added two rational numbers and I made an integer. I can do that. So we can't use the word never. They have said you can never make an integer using two rational numbers. That's wrong, right? That's false. Is this question understood? Is this clear or should I repeat? Clear. Whenever they give you a true or false question, in all of us, they'll give you at most one true or false question, right? Whenever they give you something like that, just take examples. If they say, if you can't add two irrational numbers, you take irrational numbers, root 3 and root 8, and you see if you can add them. That's how we do. Yes? Perfect. And the 12th question, What is it? What is the answer for the 12th question? Okay, guys, I'll be back. Wait. Okay, sorry for the disturbance. Right. Uh, Question number 12. Yeah. Pi is an irrational number. Yeah, pi is an irrational number, right? Right. Can you guys hear me? I got a call. Sorry. Is pi an irrational number? Yes. Correct. Because when we learn irrational numbers, the main example I took is pi. Pi doesn't end. The decimal digits of pi don't end. So that's correct. And the 13th one, the product of two irrational numbers will always be an irrational number. Is that true? The product of two irrational numbers will always be an irrational number. Okay, to check that, this is somewhat of a difficult question because you will have to check some exact values. Let's see. They are using always, the word always, which means it must always be true. If not, it is false. Let's see. I'll take two irrational numbers. We didn't teach you how to multiply irrational numbers yet. That's in the other part, but we can try. 2 times 3 is what? 6. So if I take the root 6, the square root of 6, this is also what? This is rational or irrational? Yeah, the root of 6 is also irrational. So what they say is somewhat true. They say the product of two irrational numbers cannot make a rational number. The product of two irrational numbers will always be an irrational number. Irrational, irrational, multiplied and irrational. But let me ask you this. What would you get? Shima, we know these two are irrational, right? This is not a perfect square, this is not a perfect square. If you multiply these two, what will you get? Root 36. So the roots, the square root of 36, is it rational or irrational? Square root of 36 is rational. See, I multiplied two irrational numbers and I got a rational number. I multiplied two irrational numbers and I got a rational number. Here I multiplied two irrational numbers and still I ended up with an irrational number. So we cannot say that two irrational numbers multiplied will always give an irrational number because we got a rational number also, no? See? If you take these two, the simplest examples, root 2 into root 2, what is it? Two irrational numbers multiplied, and what will you get? Root 4. Root 4. which is again 2. This is an integer. This is rational. See, two irrationals can make a rational by multiplying. Right? I hope that is clear. Okay, the last two questions. The last two questions. Question number 14. What was your answer for that? Question number 14. The sum of a rational number and an irrational number is an irrational number. Sum of a rational number and an irrational number is an irrational number. Is it true or false? Yeah, you can give your answers. They say, what do they say? If you add, sum means addition. If you add a rational number and an irrational number, they say you will get an irrational number. Always. Right? Let's see if this is true. Okay, now I need you guys to give me I'll give the example for a rational number. I'll take 3. 3 is a normal number, it is rational. Give me an example for irrational numbers. Give me an example for square root of 8. Okay, you guys say square root of 8. That is somewhat around 2.8183, something like this. Square root of 8. You said square root of 8. Square root of 8 is somewhere around 2.8. Right? So we know this is an ugly number. This is an irrational number. This keeps on going. Right? Now we are going to add these two. So we know we can add these two parts. We can add these two parts. So this becomes 5. But this part change. Is there any change made to this part? No, right? So it will be 5.8183 and so on. So still this is ugly, right? Still this is what? Is this rational or irrational? Still, yeah, still this is irrational. See, multiplication is a different case. But if you add, you can easily see that only the unit place, only the numbers before decimals get added. Or else you can put a number after decimal. Only up to a limited number gets added and the rest is the same. So it keeps on going forever. So one rational and one irrational when adding makes another irrational. That is true. That is true. Most of you have got that correct. I appreciate that. That's true. That's correct. Okay. And the final question. That is also one of the easiest questions you can come across. All the irrational numbers are real numbers. All the irrational numbers are real numbers. Is it true? Yeah. Because the largest set of numbers the largest set of numbers we use is the set of real numbers. Inside this set is every other number. Real numbers are categorized into rational and irrational. So before rational there is whole numbers. So the largest set is real number. So any number you learn is a real number. It is real. It exists. So I think you guys might not know this. Let's see. So there's a set of real numbers. So is there anything called like fake numbers or something? The topic is real numbers, right? So if there's good, there might be bad. There's light, there's dark. So if there's rational, there's irrational. So if there's real, is there something like unreal or something? Do you think there might be? No idea. Okay, so to conclude the session, I'll tell you the truth. There's real numbers, right? And out of real numbers, there are numbers, they are named as imaginary numbers. Mathematicians never rest. So they don't stop with real numbers. They go on to the realm of imaginary numbers. But that's not for us. That's for all A levels, right? So we don't touch this point. Real numbers, we stop here. This is enough. We have a lot to look after, right? Yeah, I'm coming to that. Terminating decimals. Okay. So in today's session, this is what I was hoping to cover. Now I'll give you an idea about what a terminating decimal is, and then let's end the session for today. Huh? Decimals. Before moving into decimals, let me know if everything we learned up to this is clear. If any doubts, you can ask me. It's okay, good. So in page number 3 of the tube, there's the decimal representation of a number, right? That's what I'm talking about. I'm not going to go into the details, but I'll give you a clear idea. See, if you take decimals, especially rational decimals, because irrational numbers are also written as decimals now. Irrational numbers can also be written as decimal. Pi, for example. You can write pi as something like this. So I'm talking about rational decimals. If you talk about rational decimals, there are two types. One is terminating decimals. The other is recurring decimals. You know the meaning of recurring. Recurring means repeating. Recurring means repeat. It repeats. Terminating means it ends. It's finite. Finite is the opposite of infinite, right? Finite means it has an end. So if I write 0.25, it is terminated. It ends here, 0.25. If I write 0.3, if I write 1.7, so this is the end. But if I write 0.3333, this is repeating. If I write 0.12121212, this is repeating. Now, do you get the idea? The difference between a terminating decimal and a recurring decimal? Yeah, yeah, good. Then, see, there are some decimals. See, it starts repeating here and goes up to 5. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and it continues. These are also recurring. And there are some, it ends here. So this is terminating and this is recurring. Can you see? So the basic difference is terminating decimals means they have an end. The word terminate means to end, right? To kill or to destroy, to end. So these decimals have an end. These decimals do not have an end. To conclude this, in mathematics, so we know terminating decimals can be written like this. Recurring decimals, the mathematicians, like they did not prefer writing the numbers, like writing every number, like this doesn't have an end. So what they did was, if you think they did this, they could have done this. They could have written 0.3 and kept 3 dots. So we know it like continues. But there's a small case. I'll tell you the case when I come to here, right? So what they did was they kept a dot on top of the repeating number, right? So this is what they did. This is the concise form. We'll learn this on next week in detail. This is the concise form of a repeating decimal. What they do? The repeating number, they just shrink it. Right? The reader knows now number 3 is repeating. Right? For this number, what they do is 0.12 and they keep dots on both the numbers because both the numbers are repeating. Both the numbers are repeating. Are these two clear? Okay, finally, for this 1, 2, 3, 4, 5, for this, to save their time and effort, I guess, what they did was only for the starting number and for the ending number, they kept the dots. So the reader knows it ends from 5, and again this part repeats. It ends from 5 and 1 repeats. Like this. Is that clear? Yeah. So I hope what we learned today is clear. This is the beginning of the second part of the lesson, right? So this is the beginning. So next week we'll be learning the second part. It's going to be more interesting than the first because there's no much theory. There's mathematics. There's calculations in the second part, right? So terminating means finite. They end. Recurring means repeating. They do not end. So you can complete the tube up to page number 3 with the help of these uh, data, these theories. And the recording will be uploaded in YouTube. It's already streaming live. Yeah, page number 3 you can complete. Page number 4, also page number 4 you can complete this part, right? The first part. Yeah, we can next week we can do the rest. And in page number 2 there's a Venn diagram. Can you see? There's a Venn diagram. So you can complete this Venn diagram. I drew a Venn diagram in some part of the lecture session. So you can draw the Venn diagram. I'll put a screenshot of the Venn diagram in the group. Okay, let's meet next week. I'll end this session. Bye.